Quasi-linear environments are characterized by the following ingredients. First, the set of outcomes is defined as a set of elements where each element is composed of k, that is an allocation, and pi for every player I. Uppercase K is the set of allocations. P1, Pn are called payments. The utility functions of the players are defined as the difference between two elements, where the second element is the payment, while the first element is called valuation function, and it is the value of the player over the allocation depending on her private type theta. Consider, for example, the single item auction. We have m players. Every outcome specifies the winner of the outcome and the payment of every player. We recall that the type of every player is in the range 0, 1. The valuation function of every player returns theta if the player is the winner and 0 otherwise. Thus, the utility function is theta minus the payment if the player is the winner and only minus the payment otherwise. Consider now, for instance, the case of combinatorial auctions. We have m players, we have a set of m items. The set of all the bundles is the power set of the set of the items. The type of every player is a vector specifying a parameter for every bundle. An allocation is a collection of pairs specifying a bundle and the player to which such a bundle is assigned. Notice that a bundle can appear only once, and the same holds for every player. Finally, the valuation function is just the type related to the bundle assigned to that player. In quasi-linear environments, some properties of the social choice functions are crucial. The first property is the allocation efficiency. We say that a social choice function is allocative efficient when the allocation k returned by the social choice function maximizes the social welfare. For instance, in a single item auction with 4 players, where the types are ordered such that the type of player 1 is the largest, then we have the type of player 2, and so on. A social choice function is allocatively efficient if it selects player 1 as the winner. The second interesting property is maximality in the range. We say that an allocation function is maximal in the range if it returns the allocation maximizing the social welfare of the players, given a restricted subset of allocations, such that the choice of this subset does not depend on the reports of the players. So, for instance, if the range defined before receiving the reports from the players is composed of 2, 3, and 4, a social choice function that is maximal in the range must return player 2. The third property is weakly budget balance. We have this property when the sum of all the payments is never strictly negative for every type profiles of the players. Here an example, in the case of single item auction. So if the sum of pi theta is larger than 0 for every possible profiles theta, then the property of weakly budget balance is satisfied. The last property is strict budget balance. In this case, the sum of the payments must be equal to 0. Here the case of the single item auction. So the only difference is that here we have not larger than or equal to 0, but we have only equal to 0. Quasi-linear environments are important in practice since in these environments social choice function cannot be dictatorial. In this way we can circumvent the negative result by Gibbard and Satterwhite, and we can design incentive-compatible mechanism. It is rather easy to show that we cannot have dictatorial social choice functions when we are in quasi-linear environments. Indeed, assume by contradiction that we have a social choice function f that is dictatorial. Then it is always returns the outcome that maximizes the utility of the dictator. But we can always reduce the payment of the dictator by epsilon. In this way, the utility of the dictator increases, and so we achieve a contradiction since we can improve the utility of the dictator.